Welcome everyone. It's my great pleasure to introduce Tibor Rakovszky today. Tibor is a graduate student with Klein-Coleman at the Technical University in Munich. Despite his very short PhD, Tibor has done a lot of influential work on many-body quantum dynamics already. One of the big challenges in this field is to think up toy models or tractable models where we can actually say useful things exactly. And Tibor's work was the first to show, was the first to consider a picture for operator spreading and entanglement dynamics in models of random unitary circuits. He has since considered how entanglement dynamics work with conservation laws. So in general, his work has had a great impact on this very young field, and we're very excited to have him here today to tell us about some of his recent results.
Thank you very much, all of you, for being here, and for Vedika especially for inviting me. Yeah, so what I will do today will be something like an overview of several of the things I've been working on and of the field overall. And yeah, as Vedika said, the main questions I'll be concerned with are dynamics of quantities in many-body interacting quantum systems, in particular quantities that are related to some notion of quantum information, rather than just the usual correlations, some particularly quantum correlations like entanglement. So, just as some background, the reason people became interested in these questions is mainly due to very influential experimental advances in the last 10 or 15 years. So, what people are now able to do experimentally, which was not possible before, is to really prepare quantum systems which are closed off from the environment to a very good approximation. To fairly long time, you can really follow the quantum dynamics of a system without having to worry about it coupling to some external degrees of freedom and thermalizing. And also systems which consist of many particles strongly interacting with each other. So really a many-body, fully interacting quantum problem. And also, in many of these cases, experimentalists have very strong control over many aspects of the system that they study. So you can really tune the interactions, the particular form of the Hamiltonian that you are studying, and also the initial states that you study. You have a lot of control over what initial states you can prepare. So arguably the greatest amount of work was in systems of ultra-cold atoms, in optical lattices, where people have a lot of control over what kind of lattice they create and what kind of interactions they have in the system. But there is also a lot of other setups, NV centers, trapped ions. Recently, Rydberg atoms became one of the most heavily studied version of this. So from a theory's point of view, these bring up a lot of new conceptual questions. So in particular, as I was saying, we can now prepare an initial state, which is some very complicated initial state in the quantum system, some superposition of many highly excited eigenstates of the Hamiltonian, and see how it evolves in time, and follow that evolution to fairly long times. So this is the setup that people call a quantum quench. I have some pure initial quantum state, and I evolve it unitarily. So there is some unitary, which is usually just time evolution with some fixed time-independent Hamiltonian, but also in many cases it's some driven system where you periodically drive the system by some external field or something like that. And from a theory point of view, one big question is relating to notions of thermalization. So what we expect from our studies of statistical mechanics is that if I have a system, let it evolve, wait for a fairly long time, eventually it should relax to something that looks like thermal equilibrium. But it's not at all clear how this happens in this setup of a closed quantum system, since my state is always going to be a pure quantum state, so the information that was there initially will always be there. The question is, how does it happen? Does it happen, and if so, how, that actually it's still, in some sense, well described by a thermal state? And an answer to that question, or a part of the answer, is that even though the information in the initial state is always there, if I have access to the whole system, I cannot really deduce what the initial state was if I have only access to some small part of it. So if one focuses on local observables, I should really concern myself with some reduced density matrix of my state in some small subsystem, much smaller than the whole system. And those small subsystems can really look like thermal states, parameterized by only a few parameters like temperature or chemical potential, even though somehow there is much more information in the full state. I cannot really see it if I only look at the system locally. So what I will be concerned with are questions related to how this happens. How does the system evolve from some initial state, which is very far from equilibrium, to a state which locally looks like it's in equilibrium. And one important part of this is related to entanglement. So if I look at this reduced density matrix at long times, if it indeed looks like a thermal state, it means it has a lot of entropy. It has a von Neumann entropy, which is proportional to the size of this subsystem. So it means that if I start from an initial state which has much smaller amounts of entropy, this eventual thermal entropy of the long time state has to accumulate during the time evolution, and it has to, and since it's a closed system, it can only come from entanglement. So the thermal entropy of the long time thermal state is entirely coming from entanglement accumulated between different parts of the system as it evolves in time. So this brings the study of entanglement, which in some sense is a curious property of quantum mechanics, but here it's very strongly connected to just fundamental questions of thermalization and statistical mechanics. And interestingly, it's not completely just a theoretical question of how the entanglement evolves, but recently people have been able to probe this experimentally. And the way to probe it is to consider some more general notions of entropy. So instead of the usual von Neumann entropy that is the most commonly used notion of entanglement or measure of entanglement, you can consider so-called Rényi entropies, which have some index alpha. And for different alpha, for alpha equals 1, it gives you the von Neumann entropy, but you can consider it for other values of alpha between 0 and infinity. And in particular, if you look at alpha equals 2, which is the so-called second Rényi entropy, it's related to just this quantity trace of the reduced density matrix squared. So this is a much simpler quantity than von Neumann entropy. It's only quadratic in the density matrix. And in particular, this means that if I imagine taking two copies of my system, somehow creating two exact copies of the same quantum state, then from those two copies, by interfering them, I can actually extract this information of the second Rényi entropy. And indeed, in some cold atom systems, people have actually enough control that they can actually do that, prepare two exact copies of the same initial state, evolve them in time in parallel, do some interference at a later time, and through that extract the second Rényi entropy. So this has been done in several works. These two were the earliest. And now, more recently, there are some other proposals or other actual experiments where you can extract the same information even by just having a single copy, but doing different measurements and looking at correlations between them. So the point here is that we can actually access the dynamics of the entanglement in experiments, but we are somewhat limited of what quantities you can actually measure. So even though in principle it's really the von Neumann entropy we would like to access, that's much harder. We have to consider slightly different quantities, and there's a question of, do those things measure the same properties? So this is something I will come back to later in the talk, is that one of the things we found is that even though many of the experiments sort of treat these as being equal, the second Rényi entropy and von Neumann entropy as being equivalent, they can be very qualitatively different in certain settings. Okay? So apart from the entanglement, there are also other measures of how quantum information evolves in time that are interesting. In particular, one thing that entanglement doesn't tell you is any notion of things spreading in space from one point to another. I see that the entanglement of a subsystem grows, but I would like to have some more refined notion of how does the information that was initially here, how does it spread out between different degrees of freedom. And one quantity that helps with that is what is called an out-of-time order correlator, or OTOC for short, which is essentially just, I can take two operators at 2 different positions and 2 different times and look at their commutator, but instead of just looking at the commutator, in this context, it's natural to look at the expectation value of its square. Because if I just look at the commutator, I can have a cancellation between positive and negative contributions. By taking the square, I make sure that I'm really looking at the size of this object. And what happens is that if I have a system with local interactions, which are the ones I'm most interested in, then this operator O is going to spread out within some linear light cone, assuming it's a system with not too strong disorder or something like that. And there will be a time scale associated to when this front reaches the other position X. And the speed of this front is usually called the butterfly velocity. And the reason for that is that the original motivation to look at these quantities was coming from trying to generalize the notion of classical chaos to quantum systems. So in classical systems, if I think about thermalization, one of the related notions is sort of chaotic dynamics, where information of the initial state very quickly becomes hard to trace back. And this can be reformulated in terms of Poisson brackets, and the natural quantum analog of that is this commutator squared. So purely mathematically, these 2 quantities are very similar, and indeed in certain systems, this out-of-time order correlator can be used to define a quantum analog of a Lyapunov exponent, but also more recently, the conclusion is that this only really works if the system is in some sense close to some semi-classical regime, and it doesn't always work, and you don't always get an exponential growth. But even if you don't get an exponential growth, this quantity itself is interesting in terms of probing the spatial spreading of information from one place to another. And as with the entanglement, this is also a quantity which is hard to measure. It's not a usual expectation value. So the reason it's called an out-of-time order correlator is if I expand the square of the commutator, I end up with things where I have an operator at time t times 0, time t times 0. So it's not easy to measure, but it can be done. It's something like an spin echo type experiment where I do some time evolution, do a perturbation, then sort of switch something and do a time evolution back. And this can be also done in several contexts. There are proposals for doing it in a cavity QED setup, but there are also experiments in sort of nuclear magnetic spins or trapped ions. So this is also something that is experimental relevance. Okay, and one sort of quick aside is that while I'm most interested in cases where the system actually thermalizes at long times and ask questions of how does that happen, what is the dynamics that leads you to thermalization, there has also been a lot of work on systems that for some reason or other do not actually reach a thermal equilibrium. So, and these usually come from the fact that these systems have an extensively large number of conserved quantities. So if you have a system where you have a very large, infinite in the thermodynamic limit conserved quantities, those can actually keep you from reaching the thermal state. So one example of that is systems which are integrable, which by definition have these extensively many conserved quantities. And this has been looked at in a series of very influential experiments where you can see sort of a lack of relaxation, where oscillations keep happening for very long times. And another case where you get something similar is called many-body localization, where the source of this non-thermalization is strong disorder. So if you have many impurities in the system, those can actually lead to a new phase where, unlike integrability, which is sort of fine-tuned, you can actually get a stable phase, stable against perturbations, where the system cannot reach thermal equilibrium and sort of stuck in some other state. And more recently, there are some suggestions, which both I and Vedi were involved in, of a third different mechanism for getting something that avoids thermalization due to some strong kinetic constraints on what sort of transitions are allowed in the system. Okay, good. So this was sort of a brief overview of what are the type of questions I'm interested in, or we are in the field interested in. But the main, or one important point here is that these are all very hard to study from a theoretical perspective. So most of the tools we have for studying many-body quantum systems are tailored towards studying their ground states or studying their thermal states and equilibrium, either in some field theory calculation or there are things like VMRG and or Monte Carlo, which often work for ground states. But it's very hard to do anything when you're far from equilibrium, and most of the methods actually fail. So in particular, most of the numeric, you can still get some mileage out of numerics, and they're important, but they're very limited. You can usually do some small system of, let's say, 20 spins, which is very far from the thermodynamic limit you want to study. And people use tensor networks a lot, but tensor networks are limited by the amount of entanglement, and since the entanglement grows in time very quickly, you very quickly reach a point where you cannot simulate your system anymore. And there are also analytical approaches in, let's say, field theory, but either in some non-integrable or non-interacting or integrable system, or in some holographic calculations, which give you some insight or quite a lot of insight. But still, they are very specific settings. They are very different from some generic lattice model. So for this reason, the thing, or one approach that became very useful, and this is what I've been involved with, is to try to construct artificial minimal models or toy models which capture the main features of the dynamics and sort of strip away all the details and really zoom out and have something with very few features that sort of is designed to capture just the most coarse-grained, most universal features of the dynamics. And in particular, the set of models I will talk about are called random unitary circuits, where the idea is that instead of evolving your system in time by some fixed Hamiltonian, you imagine a discrete time evolution where I have, let's say, a one-dimensional chain of spins, and I evolve them by acting on them with some two-side unitary operators. And these two-side unitaries form some circuits. Time goes up, so the more layers of this circuit I apply, the longer I go in time. And the property that makes this tractable is that each of these gates here are going to be randomly chosen and independently of each other. So this is a somewhat artificial model, but the point is that by introducing this randomness by hand and then averaging over the randomness, we actually get a much more tractable problem. And the hope is that, first of all, we want to look at quantities that are self-averaging in the sense that the averaging over the randomness actually gives you some insight into any typical realization. And if that is true, then you can also hope that it even generalizes to cases where you don't have any noise or don't have time dependence, but just have some usual time-independent Hamiltonian. So the hope is that you can actually capture some universal coarse-grained features of those as well, which is something that you, of course, at the end of the day, you have to compare to some numerics to check whether that's the case. And part of the motivation why you have some hope that something like this might work is that it is quite well known, and there has been a lot of work going past a long time, that random matrices actually describe many properties of non-random but strongly interacting quantum systems. So many properties that relate to sort of the long time, infinite long time limit are actually very well described by random matrices. And the main ingredient that's missing from these is some notion of locality, which you need to describe dynamics at shorter time scales. So by sort of combining the randomness with locality, you can hope that you actually get something that is a good, effective description. Okay, good. So what I will do in the remaining time is describe a few different results that we got from looking at these random circuits relating to the quantities I introduced earlier, the out-of-time ordered correlators and also entanglement. So let me first focus on the case of out-of-time ordered correlators. So the main quantity that one should look at is a time-evolved local operator. So we have some local operator on a given site, and we evolve it in time, and we try to follow how that evolution in the Heisenberg picture occurs. So I imagine some chain of spins, a spin 1/2 on each side, and each of those sides has some Pauli operators identity x, y, z acting on them. So this is a Pauli z operator on some site. And as I evolve it in time, it becomes some superposition of many different operators. So I can have something where I have identity z, z, identity x, y, z, or another one, x, y, y, z, and so on. So I have a full set of all possible combinations of x, y, z, and identity on all sides, and my time-evolved operator is going to be some sum or some superposition of those. And one useful property of these is that each of these so-called Pauli strings has a well-defined left and right endpoint. So if I look at this string, there is a leftmost side where it's non-trivial and the rightmost side where it's non-trivial, and away from that is just identities up to infinity. So if I want to describe how far did this initial operator at time 0, how far did it get from its initial position, I can characterize that by looking at the endpoints and the probability of getting the string with a given endpoint. So I can define a density, which is just take all of these strings and take all of the strings which have the same endpoint on the same site and look at their coefficient squared. So this is some sort of probability of going from this initial operator to something which has an endpoint somewhere here. And by the way I defined it, and due to the fact that the time evolution is unitary, it ensures that the sum over all positions of this is always 1. So this is something like a conserved density, which always integrates up to 1, but it spreads out in space. And initially, it's just a delta function at the initial position, but then as the operator goes to longer and longer strings, this will move away from 0 further and further. And so here I'm focusing on the right endpoints. I can, of course, analogously do the same thing for left endpoints. So this is some quantity that very succinctly captures how far did I get from the initial position. And what turns out to be the case is that if I try to see how this quantity evolves in time in this random circuit setup, I get a very simple description. So I have a random circuit where each of the gates are just completely randomly chosen. There is no symmetry, no extra constraint. They're just chosen randomly from all two-side unitary operators. There is a natural distribution called the Haar distribution. And what happens is that essentially the endpoint of the operator just performs a random walk when I apply these gates. So whenever I apply a gate, I have some chance of staying where I was, or moving to the right, or moving to the left. But due to the way that I set up the problem, the operator is more likely to go to longer operators than it is to go to shorter operators. And as a consequence of that, the endpoint is much more likely to move to the right than it is to move to the left. So it's a random walk, but it's a biased random walk, where there is always a net probability of moving to the right. And you can think of this as something like an entropic force, just by counting all the possible operators in the system and seeing that there are many more long operators than short ones, you get sort of an entropic force stretching this operator to longer and longer ones. So what you find is the following, that initially your density is just a delta function at some position, but then as you evolve, the right, this blue line is the right endpoint density, it moves to the right, but because it's a biased diffusion, or a biased random walk, the bias makes sure that the middle of this distribution moves to the right, but it's still a random walk, which means that it's still going to get some broadening. So the width of this peak is increasing with time as the square root of the time, which just comes from the fact that the description is diffusive. So this was a feature that was not appreciated before, and you really needed the random circuit calculation to realize this, that you don't just get a sharp wavefront, you get a wavefront which becomes broader and broader due to this diffusive process in time. And relating this back to the out-of-time ordered correlators I introduced before, it turns out that they are nothing else but just the integrated versions of these densities. So while the density is this moving peak, the out-of-time ordered correlator has this wavefront, which is 1 behind the front, 0 in front, and there is a front region, which is itself of size square root of time. So this was one of the one of the things, or the early results we learned from random circuits is that there is this diffusive broadening of the wavefront. And as I was saying, of course, at the end of the day, you really want to check that the result you get is not some artifact of putting the randomness into the system by hand. We really would like to understand properties that are there even for non-random systems. And indeed, if you just do numerics for some model which is periodically driven in time, so there is no energy conservation, but it's not random in any way. It's translation invariant and not random in time. And then you can look at this right endpoint density as a function of time, and indeed you see that this front becomes broader and broader, and it's quite well fit by square root of time. So indeed, the numerics confirm this diffusive picture that we had. So indeed, we think that this is a universal feature that should be there for sufficiently strongly interacting quantum systems. Okay, so another thing you can do, which I just mentioned briefly, is look at the same problem in a system with some additional conservation laws. So one disadvantage of the random circuit I described is that it has no conserved quantities, it has no symmetries. So in that sense, it's sort of a very extreme limit. If I want to sort of get closer to an actual Hamiltonian system where there is energy conservation, it's hard to do a Hamiltonian, but something which is in between the two cases is I can look at a random circuit and enforce it to have some conservation law. In particular, I can enforce a U1 symmetry of the total spin's Z component being conserved in time. And the way to do that is by enforcing your unitaries to have this block diagonal structure where spin up up stays up up, down down stays down down, and then up down can go to down up and back. So each of these blocks are still random, so there is a highly non-trivial dynamics, but it has this extra conservation law of the total spin Z component being conserved. And this leads to some diffusive transport. So if I just look at the total Z and I create a small excitation of the total magnetization, it will spread out in some diffusive manner. So this is independent of the diffusion of the operators front that I was talking about. This is just usual diffusive transport of a conserved quantity, which is quite generic in interacting many-body systems. But what we can ask in this setup now is how is this diffusion of the conserved quantity affect things like out-of-time ordered correlators or entanglement for that matter. And for the spreading of the operator, the picture that emerges, without going into much detail, is that you should think of your time-evolved operator as being a sum of two parts. There is a diffusive part and there is a ballistic part. So the diffusive part is the part that is really responsible for seeing the diffusive transport of the conserved quantity, which only spreads out within some square root of time region. And what happens is that as you go in time, you sort of convert from the diffusive part to the ballistic part in each time step. So instead of thinking of just creating a front at time zero, which propagates up to infinity, you are sort of creating newer and newer fronts in each time step by converting from the diffusive to the ballistic part. And what this gives you in the end is a wavefront where, apart from this diffusive broadening wavefront, you have a slowly decaying algebraic tail behind that. And that algebraic tail is a consequence of the fact that you have many fronts emitted at different times, which haven't quite caught up to one another, so they give you this broad distribution behind the actual front. Okay, so what these different works show, so this was something both we did and Vedika sort of in parallel. What this show is that sort of simple hydrodynamic descriptions can be used to understand properties of these measures of quantum information, how they evolve. So there's a nice connection there between some quantum information concepts and some relatively simple classical hydrodynamic pictures. So this was the story about how operators spread. Now, in the remaining little bit of time, I want to talk a little bit about entanglement. So when you look at entanglement, what we found is that these conserved quantities, which I introduced in the previous slide, they also have a very big impact on how entanglement evolves in the system. So first of all, one could consider this circuit without symmetries, where each gate is completely random. And the quantity that's easiest to calculate is what is usually called the annealed average of the second Rényi entropy, and where the annealed average means that you take an average first and then you take a logarithm, which is much easier to calculate than the other way around. And indeed, one can map this to something that looks like a classical partition function, average over different initial product states, and look at the result. And this is, in this case, it's actually exactly solvable analytically without symmetries. And what one finds is that it's just a completely linear growth up until the time where it eventually saturates for a finite system. But ignoring finite size effects, you just get a completely linear growth of this quantity, which is good because that's also what one expects for the von Neumann entropy in general grounds. So we were quite surprised when we found that when you look at the other circuit where you have the U1 symmetry, instead of this linear growth of the second Rényi entropy, we find something which looks linear at short times, but then curves over and becomes a square root of time. And this curving over happens at some order 1 time scale independent of system size. So just by having this conserved quantity and some diffusive transport that you couple to, it qualitatively completely changes the long time behavior of this second Rényi entropy and makes it square root of time rather than ballistic. And in fact, we find the same thing when we look at, again, one should check whether the conclusions you draw from the random circuit actually hold up in systems that are not random by construction. And in particular, what we have looked at is just a Hamiltonian spin chain, which doesn't have actually any additional symmetries, it only has energy conservation. So the statement here is that the role played by the conserved spin in the random circuit, the same role can be played by just energy conservation in a Hamiltonian. And what we find, so first of all, people have looked at this previously, the same model, and found that if I look at the von Neumann entropy, it just grows linearly in time. So the new result here is that if you look at, instead of the von Neumann entropy, you look at the second Rényi entropy, you start seeing this curving over from linear to sublinear growth. But what's more convincing than this plot is that one can notice that the second Rényi entropy is in fact upper bounded by twice the alpha goes to infinity limit of the Rényi entropies, which is just logarithm of the largest eigenvalue of a reduced density matrix. So the point here is that this quantity is much easier to look at in the sense that it's less sensitive to finite size effects. So this is something that we can study a bit more easily to longer times numerically. And in this case, this curving over becomes more pronounced, that really there is a time regime here where you don't see finite size effects yet, but you very clearly see a slower than linear and square root of t growth. So based on this evidence, we think that it's in fact a general consequence of having some diffusive modes in the system that couple strongly to certain entropies, but not to others. So the von Neumann entropy doesn't care that much about the conserved quantities, but the higher Rényi entropies, which are again quite relevant because they are the things that people can measure in experiments, those couple very strongly to the conserved quantity.
Question?
Yeah.
Does the Van Goghian entropy couple at all? I mean, do you think there will be some small square root thing at this time in a big system?
I mean, I think to leading order, it will be definitely always linear, or I think it will be always linear.
Leading order in what?
But in time. So I think it will. So here, the interesting thing is that it's just square root of time. What I can imagine for the von Neumann entropy is that it can be something like linear plus some subleading square root of time. I could imagine that, but it's not clear whether that actually happens or not. I think it's, to some extent, so one thing that I don't have time to talk about now, but one thing that we looked at is it still couples strongly if you have some inhomogeneous initial state. So if instead of doing this sort of global quench protocol, I prepare something where there's big inhomogeneities in the conserved quantity, those influence even the von Neumann entropy strongly. Okay, good. So in the remaining few minutes that I have, what I will just try to do is give a hand-wavy argument why this happens. So explain how this sub-ballistic growth of the entanglement comes about due to the diffusive transport. One thing before that, which I should emphasize, is that one way to think about this is you can think about it in terms of the eigenvalues of your reduced density matrix. So what the different entropies do is that the von Neumann entropy really measures the size of the typical eigenvalue, while these other these Rényi entropies actually really very strongly care only about the largest one. So one way to think about this different behavior between the different entropies is that you end up with some gap in the spectrum where the largest eigenvalue or the largest few decay much more slowly than the typical ones. So this would be exponentially small, while this is only exponentially small in square root of time. Okay, so why does that happen? And to understand this, it's useful to go back to the case of a discrete time evolution with a conserved spin, which is slightly easier to think about. So we have some circuit, and we evolve our state with the circuit, and we could think of this in terms of something like a path integral. So I could imagine plugging in a full set of product eigenstates between all layers of the circuit, and I would get a representation of my time evolved state as some path integral over all the possible histories in terms of the local spin configurations. And what I can do is split this path integral into two parts. There are typical histories of the system, and there are some rare histories which will be responsible for the slow growth of the entanglement. And the way to see that is that if you consider this circuit, first of all, the only way to create an entanglement between the two halves is by these gates. So only these few gates which actually cross the boundary are the ones that can create any entanglement. But because of the conservation law, if they see something where both spins are pointing in the same direction, then they don't do anything. They just give you an overall phase and no entanglement. So the only way to create entanglement is if one of these gates crossing the cut in the middle sees two spins which are not aligned. So I'm going to consider rare histories of the system where actually these two spins are always aligned and always pointing in the up direction. So these will be very rare, but on the other hand, by construction, these are histories where I could not create any entanglement. The state will be completely disentangled between the two halves. And so I end up with something that looks like a superposition of these rare histories and typical ones. And now the question is, the rare histories are rare, but how rare they are? What is the size of this coefficient? And what one can argue, based on the fact that the transport is diffusive, is that the size of this coefficient should decrease in time as something like e to the minus square root of time, rather than exponentially. So the intuition here is that because of diffusion, I can essentially cut off the system within some square root of the region around the entanglement cut. And then if I imagine that all the spin downs that could violate this polarized region here travel diffusively, I would get this square root of t, e to the minus square root of t. So given this, again, I couldn't create any entanglement in these rare histories. And then one can use something called the Eckart-Young theorem, which just says that the size of the largest eigenvalue of the reduced density matrix is lower bounded by the overlap between the full state and this rare history state. And then combining this with this assumption that comes from, or what is motivated by diffusive transport, you indeed get a lower bound, which is e to the minus square root of t. And then once you take the logarithm of this, you find that the corresponding entropy can grow at most as square root of time. And one thing that we use here is, as I mentioned previously, really all these Rényi entropies with Rényi index larger than 1 are strongly dominated at long times by the largest eigenvalue. So I can really just focus on what the largest eigenvalue is doing and forget about all the rest. That goes into this argument. And this is a somewhat hand-wavy argument, or at least there are some assumptions going into it. there is a more rigorous version, which was in a follow-up work, where if you fix your initial state to be of a particular form, then you can prove this more rigorously. Okay, good. So yeah, I think this brings me to my conclusions. So what I try to convince you is that these random circuit models are a useful way of studying chaotic, non-integrable many-body systems, and in particular that they capture some universal features that are even there in Hamiltonian systems. And what I didn't have time to talk about is what you can build in many more features sort of one by one, other than just symmetries. You could build in disorder, you could make them periodic in time. So there are many things people have looked at in this setting. And one of the results we had is that the spreading of information as measured by, let's say, out-of-time order correlators has this simple description in terms of a bias diffusion equation, which has two main components. There is a front propagating linearly, but there is also a broadening of the front in time, which is diffusive. If you add some conservation laws, they lead to additional features. In particular, there will be a very slowly decaying tail behind this front. And the same conserved quantities also change very drastically the behavior of certain measures of entanglement. So there's Rényi entropies where they grow much more slowly once they couple to the conserved quantity. Yeah, the details of what I talked about are in these papers. And of course, many open questions. You could add other symmetries which are non-abelian. You could look at systems with long-range interactions and so on. So there are many more things that you could do in this setting by building in additional ingredients. And yeah, finally, let me thank my collaborators, especially Kurt has done a lot of this work, and Frank and Shivaji. And thank you for your attention.
So in the upper right figure in this slide, so you do a random circuit dynamics, kind of simulating the condensed state. And in one of the slides, the initial state is like a pure state, right? And each color plot are like unitary matrices. So why does the entropy increase? Because like pure state, you go to pure state under unitary. So why does the entropy increase?
Right. So the entropy of the whole system is constant, it's 0. But what we usually look at is cutting the system into, let's say, 2 halves, and looking at the entropy of just 1 half. So that's why I was referring to it as entanglement, that the entropy is the entropy of a subsystem, which comes from the fact that it becomes entangled with the rest of the system.
So these random circuit models turn out to be surprisingly good models of interacting time-independent quantum systems. Are there any features that you thought they would get right that they actually get wrong?
That's a good question. I can't really think of an example where there was a very...
They're all bound, so bound to not adhere to the bound.
I mean, I think there are features that they cannot capture for sure, but those are probably the ones that you already sort of know by looking at it, that there are, like, say, certain types of dynamics that are hard to, like, if you wanted to understand. So for example, one thing is there's this many-body localization that's hard to get in some sense in these circuit models because they are just so strongly scrambling information. You can still do something like this, but you have to sort of fine-tune the ensemble of random gates to get something like that, to have sort of weak interactions in a way. But I'm not sure how surprising that is. So there are certain things that are hard to capture with this, for sure.
It's also the role of finite temperature, for instance, is hard. That's why we're building these conservation laws. But again, that's something that we knew at the outset would be hard. So it's not surprising. Other questions?
Is it clear that the diffusive broadening should also be a feature of non-disordered or regular Hamiltonian systems?
Well, I'm not sure if it's clear. We see evidence of it in numerics. Intuitively, the way I think about it, it's a similar question to why just regular transport is diffusive. Like if I look at regular transport of energy or charge or something like that, it's very easy to get diffusive transport by putting in noise by hand, but you also get diffusive transport just due to interactions, even without noise. And I think the source of the diffusive broadening here is qualitatively similar.
Are there any sort of ideas perhaps might be extended into, say, an open system or driven system, using sort of the random circuit?
Right. Yeah, I have open systems here as one of the open system is an open question. So yeah, I think definitely you can do that. One very particular type of open system that people have started to look at a lot is if you imagine that you do this unitary dynamics and sometimes you also do measurements. So that's something that people looked at in the last 1 or 2 years quite extensively. There are some very interesting properties that happen when you sort of have two competing mechanisms. You have the unitary evolution that creates entanglement, you have the measurement that removes entanglement, competing with each other. But I think you could also look at more traditional types of open system dynamics by just coupling to some extra degrees of freedom and integrating them out. But I don't think this has been looked at too much. And you can also look at driven systems in the sense, and that has been done, that you could make your random circuit periodic in time, which is a bit more close to a driven system.
So you talked about sort of the energy transport and the entropy behavior, but I'm wondering actually sort of those are convenient to calculate, but not necessarily the most natural experimental observables. So are there proxies that would kind of let you see the same behavior that are like even more direct observables and like spin correlations?
So which behavior do you mean?
Right now I'm thinking of the case where you had this diffusive energy transport with a linear growth in entropy. Like what would be the simplest thing?
Right. I mean, if you just want to see the fact that the transport is diffusive, there are definitely much simpler things to look at. Like here the question we were asking is more like assuming it's diffusive, how does it affect other quantities? If you just want to see diffusive transport, I think just regular, let's say, time-ordered, unequal time correlation functions, how they decay, is a relatively simple thing you can calculate that would tell you about that.
And so if I want to also see the entropy behavior, is there something simpler than directly measuring any entropy? Is there that would be indicative maybe of that linear graph?
That's a good question. And I don't know what the answer is. So in a way, the question is whether you can, for example, extract the largest eigenvalue of your reduced density matrix by some simpler measurement. I think that might be possible, but I don't really know how to do that.
We actually started the first quantum information story.